welcome to another episode of Dave Does Math from Home. Today's episode of Dave Does Math from Home is about section 15.5. We're skipping 15.4, it's not entertaining. 15.5 is good though. 15.5 is high quality entertainment for you and the entire family. Get some popcorn, this is going to be great. We're talking about gradients and directional derivatives, which is kind of a whole new thing. We know about partial derivatives, and I said in the partial derivative video that there's no such thing as like just a derivative. That's not a thing that exists in Calc 3 in 3 dimensions. You have to be going in some direction or another. The gradient is the closest thing we have to some sort of like neutral, non-directional, entire, not partial derivative. And we're going to get there with vectors. So let's start with a pretty simple function. Let's do f of x, y equals x squared plus y squared. This is a paraboloid. Hopefully we remember doing a level curve of this guy. It's like if you take a parabola and spin it around 360 degrees around the y-axis, you get this paraboloid round shape. It's very nice. We know from the last section that the derivative with respect to x, which is sometimes called f sub x, is 2x. And we know that the derivative with respect to y, which is sometimes called f sub y, is 2y. So here's how we're going to get the gradient. The gradient, which is usually written as delta f, not delta, del. Delta is a triangle with the base flat on the bottom. So this is the del. It's like a triangle that points down. This is how we write the gradient of f. And the gradient of f is f sub x I and f sub y j. So you take the partial derivative with respect to x and you attach that to the unit vector I, and you take the partial derivative with respect to y and you attach that to the unit vector j, and now you have a gradient. And the gradient is, for us, the gradient is 2xi plus 2yj. And now we should pause for a moment to contemplate what this means, because this is, for us, a brand new kind of thing. We have never seen a thing like this before. We have seen three-dimensional functions where you plug in an x and a y value and you get a height, and as you vary the x and y values you get a surface. And we've seen vectors that involve i's, j's, sometimes even k's as well, and numbers attached to them, so that they're always, I, j, and k are always giving you a vector. It has a constant magnitude, constant direction, because it's a bunch of numbers involved. This is some weird combination of those things. This is a function that we can plug in x and y into. But when we plug x and y into this function, we get a vector. We're not getting the height. We're not getting a z value. When you plug in x and y, you don't get your third coordinate. When you plug in x and y, you get a vector. Or alternatively, you can think of this as a vector that has variable quantities in it. It's not a constant length, width. It's just variables. So the size and direction of this vector are going to change. This is called a vector valued function. which is a super fancy way of saying that it's a function. You plug x and y into it, and the output is a vector. Vector valued functions do very interesting things when you graph them. So I want to graph this one for a little bit so we can see what it looks like. I'm going to erase some of this supporting stuff so I have lots of room to draw a really big graph. And we'll switch markers so I have a very robust color. Let's try this one. If this is f of x, then the gradient of f is 2xi plus 2yj, and we are going to graph that here. So, I'm just going to pick some numbers, and we'll do vectors. If I plug in 0, 0, I get the vector 0, 0. If I plug in 1, 0, I'll get the vector 2, 0. If I plug in 0, 1, I'm at this point. 0, 1 is the coordinate of the vector, or the 0, 1 is the coordinates I'm putting in, and it creates a vector that goes 2 units up. This is, I plugged in 1, 0, that's the point that I used for x and y, and it created a vector that from there moves 2 units right. This is 2j. Similarly, if you plug in negative 1, you'll get a vector that goes this way, negative 2i, starting from negative 1, 0. And if you plug in 0, negative 1, you'll get a vector that goes 2 units down. This is negative 2j. So let's plug in some mixed numbers as well. Let's do 1, comma 1. If I plug in 1, comma 1 as the input to my function, the output is 2i plus 2j. If you plug in this, negative 1, 1, we get a function that goes negative 2i plus 2j. Hopefully the pattern is pretty clear. At this point you're going down that way, and at this point you're going down this way. What about something like 2, comma 1? If you plug in 2, comma 1, you're out here, you're probably going to go 4 over and 2 up. 4i plus 2j. If you plug in 1, comma 2, you're going to be going 4 up and 2 over. 2i plus 4j. And you could, hopefully you can imagine me continuing this any point you want. We can plug in negative 1, comma negative 2. It's going to go down negative 2i minus 4j. And you could keep going if you like, if you want to complete this picture, make it really pretty. I encourage it. It should be fun. This is called a vector field. Vector fields are going to be an extremely important tool for us as we model physical activities. Vector fields are a way to model and describe and draw situations where you have variable forces pushing in variable different directions across the entire plane. And there's a lot of different things we could do, we could model with this. This particular vector field is, I like to think of this as like the sunburst. Everything is pushing outward from the center, and the strength of its outward push is proportional to how far away it is. So all these points right in the middle are pushing directly away from the origin, very slightly, and as you get further out, you're pushing directly away from the origin much more strongly. We could make vector fields that spiral. We could make vector fields where everything is being pulled into the center. I like to think of those as like the black hole vector fields. And we could make those in 3 dimensions as well. If you really want to talk about like a black hole kind of vector field, we could make a vector field f of x, y, z is negative xi minus yj minus zk. This is a vector field in, I should say this is not a vector field. This is a vector space, like a 3-dimensional version of this, where at every single point, the vector you get is pushing directly into the origin. I guess this isn't quite the black hole thing, because this pushes you into the farther away you are, the harder this pushes. If you want to divide this by x squared, yeah, I guess you'd have to do like 1 over x, and 1 over yj, and 1 over z, k. This is still pushing you directly towards the origin, except when you're far away, the push is very small, and when you're very close, the push is very strong. So this is probably more accurate to a black hole thing, black hole situation. The closer you get to the origin, the stronger it pulls you into the origin, and it's always pulling you directly towards the center. So this is a vector space. This is a vector field. Vector fields and vector spaces are going to be especially useful when we start modeling electrical current, or we're going to use this a lot for like water current. Like if you have water flowing through a pipe, or water, the really interesting thing is when you have water flowing through a grate. Like there's some sort of flow, because when you have water flowing through a pipe, the strength of the flow is stronger in the center of the pipe than it is around the edges of the pipe. So that's a great example of when you need to represent variable strengths based on the position. And we'll later, much later in the class, we'll get to these situations where we're going to want to model water flowing through a pipe hitting some sort of surface, some semi-permeable surface like a grate or a strainer, maybe. Maybe we'll do a problem about spaghetti. We're gonna run water through a spaghetti strainer. But we can model sort of the resistance that semi-permeable surface is going to have against that flow through it. And if you've heard me say the word flux integral before, maybe in class, that's what that is. Flux integral is about the flow of a vector space through a surface. So this idea, vector fields, vector spaces, it's gonna keep popping up. You're gonna see this a lot. Right now, we're not going to do too much with it. We just kind of need to know what they are, what they look like. If you need to graph one, you can just start plotting a bunch of points and seeing, based on the points you plot, figure out where the direction, where the vectors are, how big they are, where they point. You can graph a handful of vectors like this. You can get a pretty good idea of what the vector field looks like in these cases. And we need to tie this back to the idea of gradients. So the gradient is a vector field, always. Because you're always going to get a function that depends on x and y as a vector that gives you this vector field. The interesting thing to note about gradients, though, is that they tell you gradients are a special kind of vector field that tell you a bunch of really important information about the vectors themselves, or I'm sorry, about the function itself. So this particular vector field has some properties based on this function. Remember that this function was the paraboloid that goes up. I think the first big thing that I want to note about this gradient is that if you picture a vector field like this, sort of like, or I guess picture, based on this vector field, try to picture the paraboloid coming out of the board at us, at the camera. At every point on the vector field, like this point right here, that corresponds to part of the parabola that's arcing upward and outward like this. These points right here, at that point the parabola is arcing outward this way. At like these points, the parabola is arcing this way. Hopefully my gestures are coming through well on the camera. At this point it's arcing out this way. So one thing that we can hopefully see by looking at this vector field and imagining the paraboloid that it came from is that all of these vectors are pointing in the direction of steepest ascent. So if you imagine the parabola coming out at you, at any point on that parabola, if you were standing on that surface and you wanted to go in the steepest possible direction upwards, you can always follow the direction of the gradient. The other very important thing to know, and sort of a consequence of that the gradient will always point in the direction of steepest ascent. The consequence of that is that level curves are always perpendicular to the gradient. So the level curves of x squared plus y squared equals, they're just z equals the radius squared. So the level curves for the paraboloid are circles, concentric circles, getting larger and larger out from the origin. And at any point on this circle, the gradient is always going to be perpendicular. Which hopefully makes sense, because if you think about the level curve, imagine once more that you are standing in the surface of this paraboloid. You're standing inside of this giant bowl shape. If the gradient tells you the direction of steepest ascent, opposite that direction is steepest descent. So if you face the gradient and go forward, that's the steepest possible path ahead of you. If you walk backwards, that is the steepest descent. If you turn exactly 90 degrees from the gradient, from the steepest path, and walk in that direction, right in between steepest ascent and steepest descent should be whatever keeps you flat. And that's what a level curve means. The level curve is, this is all of the points that have the same height. So if you're on the surface of this paraboloid and you're walking around the level curves, that's you doing a circle that does not change elevation at all. You are not ascending, you are not descending. And at all points, perpendicular to that level curve, perpendicular to the stay flat path, should be steepest ascent path and steepest descent path. So that's some really good information we can extract from gradients. And I'm already at 19 minutes. This has been, hopefully, an incredibly illuminating theoretical discussion of gradients. I am going to make a second video, a part 2, where we just do more gradients, do some examples, and then we still need to talk about directional derivatives. Stay tuned, there is much more to come.